chemical program, or if you have you're putting in a new system, we'll talk a little bit about things to talk about and look at. So what are they? There are these metals or metalloids that are toxic to microorganisms. And these are, does anybody know what those are? From your old biology days?
This looks like a water bear.
Yeah, something like that, yeah. I think they're copepods. But a lot of times when they do those toxicity tests, they use daphne, magna, maybe another small water flea like that. So we look at the periodic table, and here's some of the cast of characters we're talking about. Actually, that doesn't look quite right. Those red circles are supposed to be up a little higher. So we're talking about chrome. Not as much chrome as there used to be out there, but people still use it in especially military applications. There's a lot of chrome still being used. Nickel, really popular. Copper, zinc, all three of those are pretty prevalent out there. Silver, cadmium, palladium, gold, lead, what am I missing? Selenium. Primarily it's the nickels and zincs, coppers of the world. Again, sometimes chrome. We'll talk a little more about detail into chrome in a bit. Did I miss anything? Anybody treating anything exotic out there like molybdenum or selenium? Which one are you guys getting hit with? Molybdenum. That's not an easy one. Not an easy one to get rid of. We'll talk about that in a minute. And yeah, this is supposed to be moved up. I'm not sure what happened. But selenium and molybdenum are the ones that are kind of the new heavy metals that the environmental agencies are starting to kind of crack down on a little bit. You know, the power industry, you know, copper piping. I've got some customers that have higher copper coming in their plant than they do going out because they have copper piping. Sometimes they've got galvanized piping. Sometimes their nickel's higher or zinc is higher than coming in than it is going out, believe it or not. You know, this is a shop where they're doing putting paint on parts. Obviously, they're digging for some kind of heavy metal there. Any of the plating or the printed circuit board shops, a lot of copper in there. And this is just a plating bath. So all kinds of industries, I'm sure we're missing some. So what happens? So these things bioaccumulate. You probably have heard that term before. So they go into the sediments after they're, you know, going into the watersheds, and these zooplankton, you know, daphne magnas, the water fleas, what does he call it, water bear? All these different microorganisms or zooplankton are eaten by fish and then by birds. And sometimes we eat the fish and sometimes we eat the birds. And that's not good for us, especially if you're a pregnant lady. So obviously some of these metals are worse than others. You know, cadmiums and mercuries and leads are really, really bad. And you don't see those very often, and chrome. But chrome's really easy to treat. So we got to get them out of the water, right? We got to pull them out by precipitating them. Otherwise, they stay soluble and they don't come out. So we have a solution that's full of zinc, let's say, and we add our precipitant and we precipitate out a precipitate. So we're pulling that metal out of solution. A couple ways of doing that we're going to discuss here in a few minutes. All right, hydroxide precipitation. Most people, this is what they do. Not always the best in terms of overall results, but if they're using it, they probably don't have real high heavy metals to begin with. So yeah, here we go. Our old friends, the pH analyzer and the pH probe. This is why pH is so important. You've got to have equipment that is calibrated and works, or you're going to have, and in particular, when you're treating heavy metals. So we have a situation where we have lead and we have chrome. two very different pHs. Can be a problem for some people if they have metals that precipitate out at different pHs. So if you look down on the bottom there, so where is chrome going to come out? About at 7.5, whereas lead maybe more in that 10 range. So you can see where there might be challenges for some customers. So what do? You treat for the one that is giving you the most problems, and you hope for the best in some of these other things. So when we talk about hydroxide precipitation, we're talking about a very, very closed lab environment where they're coming up with these curves. So in the real world, let's pick chrome. In the lab environment, it says 7.5 is the best pH. Well, at your facility, with a mix of chemicals and metals and everything else in the water, it might not be 7.5. It might be 8 or 8.5. So one of the things that's important that we do is we look at in the real world, where's the optimized treatment, and some of these things are really great to use to get you in the ballpark, but to really help you out, you need to do it on site. So amphoteric, does anybody know what amphoteric means? Maybe you did at one time and you just forgot, right? So when we look at chrome as an example, you see that it comes down, and the best or the lowest concentration of chrome is 0.1. And then as you watch as the pH goes up, it goes back into solution. That's what amphoteric metals are. They kind of have this kind of U-shaped form in terms of their solubility. And some of those are pretty tough. Chrome is actually one of the easier ones to treat. So, and this is kind of a joke, if you're really interested in what the solubility constant is, anybody want to read that? I'm kidding, probably not. It's one of these things that's mind-numbing. If you really want to know what a solubility constant is, you can check this out. So, okay, what are the advantages of hydroxide precipitation? Relatively inexpensive, and if you have a ton of metal, it's really easy to treat in most cases. What are the disadvantages? If that pH changes, if you have that sludge stored in a sludge thickener, that pH may change, and those metals may resolubilize. So you may have a higher reading when you're running, as an example, running this waste through your filter press. So what's coming out the filtrate may have higher levels of these metals than you would like. And it does create a lot of sludge. But again, if it's not a F006 listed hazardous sludge, that might be okay, because you're just putting it into a dumpster and it's not that expensive anyway. Yeah, like I said earlier, it's, some of those metals might be way off in terms of where their solubility or insolubility is. One might be at a pH of 6 and one might be at a pH 11, and that's makes things difficult. And again, you got to have a pH probe and an analyzer that are calibrated and working, or you're going to have a big mess on your hands. And I can't tell you how many times I work with people and they have issues, and the first thing I ask them is, what? You guys know what I always talk about. Did you calibrate your pH probe, right? When's the last time you calibrated your pH probe? And if it's off by 0.2, we're okay. But if it's off by 2 points, you can see what can happen. Not good. So the second type of metal precipitation is sulfide. Again, uses the solubility constant to precipitate it from the water. So basically what that means is they take the highest concentration of metal that they can get, supersaturated solution, and then they treat it. So that's basically what all that gobbledygook was about. I'll summarize it for you. So all of these metals, and if you take a look at the left-hand side, is that the X or the Y? I forget how that works. I think that's the Y, right? That's the X. Okay. So the X side of the graph here, look at how low they can go. We're talking about, on the bottom, 10 to the negative 13th. So what does that tell you about sulfide versus hydroxide? Well, I'll tell you what it means. If you have really, really low metals limits, you may have to use sulfide precipitation because it's the only thing that will allow you to get to some of those really, really low numbers, like a 0.01 or 0.0 anything. You may almost have to go to sulfide unless you're really lucky and your hydroxide precipitation works out real well, or you've got filtration or other things. So, and on the other side, there's actually two different types of sulfide precipitation. You can use an inorganic and as well as an organic form of sulfide. And we'll talk a little bit more about that. But in general, if you really need to get those numbers down, sulfide may be the best option for you. And again, I threw that in there because I know it's mind-numbing, and if anybody really wants to read that, feel free. So there's the inorganic sulfide. So less pH dependent than hydroxide precipitation. So you can not ignore your pH probe, but you can, it's not going to be as critical. Very, very common. You just don't create as much sludge. And those metal sulfide complexes, if you're running the sludge from your sludge thickener through your sludge press, if someone's doing a T-clip, you're going to be okay. Whereas with hydroxide, it might not be exactly what you thought it was, because that metal might be going back into solution. So sulfide is it forms a really insoluble complex, which you can't say with hydroxide. So slightly more expensive than hydroxide. We do have challenges because of the odor that comes off. I know I have customers that have issues with odor that they have to put equipment in to take care of it. It can be a little bit of a handling issue. It kind of turns your fingers black and things like that, which, isn't a huge deal. So then we have this other thing called organic sulfide. So one of the benefits is if you do have any chelants in the water, really, really good at breaking those chelant bonds. And we're going to talk about chelants in a second. And really, if you have kind of a neutral pH, it'll pretty much complex with any metal at that pH. Less sludge than hydroxide. Again, relatively pH independent. And if you're running that sludge through a filter press, you don't have to worry about those metals coming back out. Really low. So disadvantages, again, slightly more expensive than hydroxide. I've done some analysis comparing the two different forms of sulfide, and they're very close on a performance basis, organic versus inorganic. On a per pound basis, the organic is more expensive than the inorganic, but on a treatment basis, very, very similar. And there are some slight handling concerns with the sulfide. But again, just to kind of recap, you want really low numbers. You're worried about your metals. Sulfide is really something to consider. All right, what about those metals that have more than one valence state? And some of them have a ton, which makes treatment, more difficult. I mean, chrome has a whole bunch. Nickel has several, copper a couple. So it's important to know what valence state some of these metals are in. Sometimes they might need to be reduced so that you can treat them. Chrome as an example. You cannot remove trivalent chrome. Impossible with pH adjustment or sulfide or anything. So you got to reduce it from, I'm sorry, hexavalent chrome. You can't remove. Trivalent has to be converted to trivalent chrome, and we're going to talk a little bit more about that in a second. But the valence state is another thing to really kind of keep an eye on. Selenium is one of those new metals that's starting to get attention. And we were working with an engineering consulting firm that was doing some work on this for one of their clients. And really what they were able to do is use what's called zero valent iron. And they were able to convert that selenium to selenite. And selenite is the only form of selenium that can be removed. So we had some, pretty good results with that. So anyway, zero valent iron is kind of a newish thing, and it's something to consider if you have a lot of selenium in your water. Molybdenum is a really tough one. And a lot of people, as a water treatment company, we used to use molybdates quite often in our cooling tower treatments. Very good corrosion inhibitor, but it is just so hard to get out of water. Very difficult. Maybe you can get it out using this zeolite, which is like a resin that's coated with these magnetite nanoparticles. But depending upon what valence state it is in, very, very difficult to get out. So I say, if you have molybdenum, you probably need to figure something out. Maybe evaporation is one of the best ways. Unless, Joe, you've got some better ideas on that. We'll talk a little bit more about this in detail. So I mentioned those keylets earlier. So what keylets do is they attach their organic molecule that attaches to the metal. And it's very, very good at keeping the metal soluble, which in our world is the last thing you want. You don't want that metal to be soluble. Because what happens if the metal is soluble? It's not going to come out, right? So EDTA, sodium gluconate, these are things that you'll find in your plants. Ammonia, phosphorus, hypophosphite, very, very prevalent in metal finishing when you're talking about electrolytes, nickel electrolytes, copper, those kinds of things. That EDTA can really make your life miserable. Also known as a sequestering agent. But again, these things are all designed to keep metals. These are our enemies. These are designed to keep metals soluble. All right, we talked a little bit earlier about the chrome, and I mentioned that you have to convert it from hexavalent to trivalent. And basically, what we do is take the pH down to about 2 or 3, add bisulfite, sodium bisulfite. Take that ORP to about 250, actually it's negative 250. Using the ORP analyzer. Does anybody do this, by the way? You guys don't really, you've probably done it, but you're not doing it now. Yeah. And then you raise the pH to 8 and 9, and that chrome, it's kind of an interesting reaction because the hexavalent chrome is yellow, and the trivalent chrome is a pretty blue. Remember that video I had earlier? Was a beaker on there, and it was that blue color. That's kind of what trivalent chrome looks like when when it's ready to be precipitated. And then the most important thing to note there is you can't get hexavalent chrome out. You've got to convert it to trivalent. That's the takeaway on this one. Electrolyte nickel becoming more and more popular in a whole bunch of different industries, plating industries. The hypophosphate is really the toughest thing that we have to deal with in ammonia. And in some cases, people will take their baths and just plate them out. They'll put steel wool in there, and they'll plate out their remaining metals right on the steel wool. Has anybody ever seen that? Yeah. Oh, you have, Rob? Electrowinning. It's one way to do it. Had a big plater years ago that was able to meter in their electroless nickel, the real low content, and we were able to treat it, but it was not easy. So anytime we have these electroless nickel compounds, a lot of times people will just send them off site to be treated. But if there's enough flow, you can kind of bleed them in slowly. And you know, back in the day when nickel was the London Metals Index for nickel was really high, it was like $18 a pound. You could actually take their sludge and you can send it in, and they were getting paid for it. So if you have high nickel content in your sludge or copper, you can actually, you know, generate some revenue off the sludge, which is kind of unusual for a wastewater situation. Don't get to do that very often. So one of the things I wanted to highlight here, and some of the things I talk to a lot of my customers about, is if they have issues, I say, well, what's the problem? Well, is the metal soluble or is the metal insoluble? Because if it's insoluble, that's different than if it's soluble, right? So one of the things that you can do is get this mill-pore filter apparatus, and technically anything that's 0.45 micron or lower is considered soluble. So these metals that are getting through their system would actually go through that filter. So the metal solids that are insoluble are going to remain on the filter. The stuff that is not is going to go through it, right? So I can say, okay, guys, you must have a keylent in there, or something has happened. Your pH is off if your metals are still soluble, right? Does that make sense? If it's you running through the filter and there's nothing in the filtrate, well, then you're having a physical problem. So you might not have appropriate settling in your clarifier. Maybe things are just, your solids are too, solids in your clarifier are too heavy, or maybe you're having issues in your sludge press. So a whole different set of reasons why, just by doing a simple solids versus insoluble test. I don't know if anybody's ever done that, but it's very good at diagnosing, you know, where the problems are coming from. All right, we're going to move on to equipment. So you guys have seen those already, right? Little batch treatment tank. This is mixed media filters. Got some canisters there full of resin. And our old friend, does anybody know what that is? Ultrafiltration or RO system. So batch treatment is pretty simple. You know, you have that equalization tank. If you have an equalization tank, not everybody does. Sometimes they'll just use the batch treatment tank as kind of the equalization tank. And you're going to treat it with your chemistry, and everything that's going to happen is going to happen within that tank. So it's really, you know, the reaction that takes place is very centralized. You don't have to worry about anything going whisking through like a continuous flow system. And a lot of times, most of the time, we're using our old friend, the plate and frame filter press. Yeah, really, again, it gives you the maximum control over what it is you're trying to treat. Flow through system, a little different. You know, flow is larger than 10,000 gallons. We can easily control the pH most of the time, as long as the pH probe and analyzer are working, right? Chemicals are metered in, and all this stuff is happening, you know, on a continuous basis. I mentioned the seating is an option. I know that's maybe hard to believe, but sometimes when you have a very, very low metals content in your water, it makes it hard to treat. It's just because there's nothing there for things to kind of grab onto. So seating is an option. What that means is you take waste from your sludge thickener and maybe pump it back to your first pH adjust tank. So then you at least have some solids that you can use to help give it some weight, and all those metals can kind of contact one another, and it makes it a lot easier. So I always, or ideally, you have 10-minute residence time to adjust pH. Again, in this kind of wastewater treatment, pH is really important. If I haven't said that enough, if you come away with one thing today, is make sure your pH meters and probes are set properly. So, another thing that you can use on the back end of your clarifier is a sand filter. It can work really great. Pull out those little particles that are getting through, all those insoluble particles. The sand is backwashed, goes back to the front of the system. It's really a nice way to help you control your situation. If you're hydraulically limited, you've got a lot of flow, and your solids on your effluent are pretty high. Good way to do it. Only challenge can be oil. You get oil in a sand filter, and that is not good. So if you have really heavily oil laden waste stream, you gotta be real careful. Right, Joe? And sand filters cannot remove soluble metal, right? So what's going to cause that metal to be soluble? So if you use a 0.45 micron filter, you would be able to figure that out. But what could cause that metal? There's a couple things. What could cause that metal to be soluble? Or
the valence state.
The valence state, yes. Yeah, pH, valence state. I didn't even think of that one. That is definitely, that is a poop emoji worthy answer.
Thank you.
You're welcome. What else? What are these things that complex with metals? Starts with an E, ends with an A, and has a D and a T in the middle. EDTA, or any of those other things. So, if you have high ammonia, you might want to consider using sulfide precipitation, All right. Ion exchange resin. If you have really, really stringent effluent restrictions on your discharge, this is something to consider. Now there's special resins you have to remove. Some people will just use these on a standalone, but real small plants will use these. What happens is they drop off these cylinders. You use them, fill them with whatever metal it is that you are trying to remove. They'll come in and they'll take them and they'll clean them off site somewhere and then bring them back. But if you have a real low metal on something, zinc, nickel, you might want to consider using these as a polish. You guys ever get involved in this kind of stuff? Yeah.
Not too much.
Okay. But this little guide on the bottom left gives you an idea of where this resin is economical and where it's just way too costly. And basically it depends on how much metal you're trying to pull out. But in some parts of the country, whether if someone was discharging to a river that had heavy metals, they may want to use this kind of equipment. RO, becoming very, very popular, becoming very, very more reasonably priced. A lot of people are, interested in using ROs, not so much here for water reuse in the Midwest because we've got all this water. But in other parts of the country, reverse osmosis has become really, really popular. For a corporate guy, you might, in some parts of the country, you might say, we might want to reuse our water, and an RO could help you do that. One of the things that's really interesting is when you look at the rejection rates, everybody thinks RO takes absolutely everything out. Guys, it's not true. There's still a lot of stuff. Like selenium, what was the one I was looking at? Cadmium, the chromate. Look how much chromate can still be in the water after they're treated. So again, everything has its place. Not everything is perfect, but in combination, some of these technologies can really help you get to the end goal. All right, chemicals. really, the most prevalent, of course, are the sulfuric acid. 93%. So sulfuric acid is the highest you can get, or 66-degree bomb A, and that is the one that's used most prevalent. And again, hydrochloric acid maybe for cleaning, but not for treating. As I mentioned earlier, lime has become really popular. Now, is it easy to handle? Jake, is lime easy to handle? Not always, no. Caustic is easier, but caustic is also very dangerous. So there's some benefits and negatives to everything, and you got to find out the one that works best for you. This is just a kind of a chart showing, what are the dosages or relative dosages of some of these coagulants. All of these on the left-hand side. The only one that is alkaline is sodium aluminate. Anybody ever used sodium aluminate for a treatment? It is the only alkaline coagulant that I'm aware of on the planet. In some cases, it works really well. It just depends. These are the precipitants. There's a lot of them. Hydroxide, of course, is the most prevalent. The DTC or carbamate is one that our company sells a lot of, as well as the hydrosulfide for the sulfide precipitation. The TMT there, I don't know who uses that. I've tried it on I don't know how many applications, and it never seems to do anything. So I don't know who uses that. Thioret is another one that we sell. It's it's similar to, I guess you could say, to the sodium sulfide, hydrosulfide. The only problem with that is the odors. Most of the time in our world, we're talking about an anionic that is, medium molecular weight, medium charge density. In the metal finishing world, that's kind of the ones we use. Our 1336P is one of the products that a lot of you people are using. It is like the standard for the industry. Very, very popular. Emulsions that are similar to the 1336P, which are that medium molecular weight and that charge density, we sell quite a bit of that too. But very, very uncommon to see a cationic flocculant out there in a metal finishing application. Extremely rare. Does anybody know why? We go way back to that's one of them. What is the other thing? Most of these metals are coming out at a pH higher than 7. And where do the cationics work best? Anybody? Was that? 7 or below. Exactly. All right. I'll give you a poop emoji for that. You're welcome. So when we're talking about designing a program, let's say you're building a new facility or you're bringing in a new piece of equipment, that maybe you need to look at a whole new lineup, whole new treatment system. So treatability study would be one thing that you would want to take a look at, where we grab samples and do the jar tests up front. But the things you're going to want to look for in particular is how can we equalize this waste stream, make it easy to treat. When we have a system that looks like this, when we have these big, huge, ups and downs, where we have solids all over the place, maybe the flow is somewhat, level. But if we have solids all over the place, how much fun is that going to be to treat? Not a lot of fun. We're shooting for shooting at a moving target. And that's never easy. So whenever I see a system or somebody asks me, we're putting in a new system, the first thing I ask them is, what about equalization? How much equalization are you going to have? If you have 100,000 gallons to treat, at minimum, you'd like to have a 50,000 gallon equalization tank. Ideally, you have a whole day. Not everybody's willing to spend that, are they, Joe? It's just makes everybody's life easier when you have the ability to equalize. So it looks a little bit more like that. We don't expect perfection, but it'd be nice to make things a little bit easier on ourselves. So, again, critical mixing. The coagulants, they need to be mixed properly. If they're not mixed properly, you're not going to get the full effect of the benefit of the product. Injection points, sometimes you can move them way back. So sometimes you don't have any options. Put a lot of options in your system so you know where the optimal place is for that coagulant to mix or for that flocculant to give you the best benefit. pH meters. I think you guys know how I feel about that. Solids loading in general. How are you going to handle the sludge? What are you going to do? Is it F006? Is it hazardous? Is it not hazardous? Is it going to go in a box? Is it going to go in a big 20-yard dumpster? What are these metals that we're talking about? What about keylets? Is there going to be any keylets in this stuff? Even if people are looking at new cleaners and things like that, I always ask the question, what's in the cleaner? I need to see the SDS before I say we're good to go. Can you recycle the metals? We had that situation where there was a ton of nickel in the sludge. Actually gained some benefit. Maybe there's opportunity there to actually produce a profit. So this new line is going to go in 5 years later. Are you planning on expanding it? Well, then let's size things so that you can handle that extra flow, things like that. And as I always tell everybody, maybe it's not the EPA, but your local, DNR or regulatory body, you always want to be on good terms with those people, because if you get on bad terms, that's kind of hard to turn that around sometimes. All right. Will a sand filter remove soluble metals? Yes or no? Are you sure? Right answer. You don't have one of these yet? I think I should paint one gold. I have a gold poop emoji award. All right. So pH is not important when precipitating heavy metals. True or false? False, yes. If you don't get that one right, I'm in big trouble. RO will completely remove all heavy metals. True or false? Right. A precipitant will precipitate metals as sulfide so they can be easily removed. A precipitant like what? Nobody? How about a carbamate? DTC, sodium hydrosulfide, all of those are products that can be used to pull metals out in the sulfide form. What are the two methods of removing heavy metals? Ooh, the brains are churning on this one. It was right in the beginning. Two different kinds. Pardon?
Microfilter?
Nope. The methods of removing heavy metals.
Hydroxide precipitation and sulfide.
Jerry, that's definitely worthy of a. Since he's the new guy,